All right, here we go. So, exponential functions, what you guys just got done with in college algebra or are doing right now in college algebra. Same stuff here. Exponential, logistic, and logarithmic functions. We'll look at exponential and logistic first today. All right, so we'll look at exponential functions and their graphs, the natural base, log base e, and then logistic functions, which are a little different, and then populations. Okay, an exponential function is ab to the x power. The variable is the power. That's an exponential function when the variable is a power. Okay, so the initial value is a. So if you have a starting value, that's a. That's a. Okay, b is the base of the function. Excuse me. B is the base of the function. And obviously, x is the exponent. Okay, that's the power. So the initial value is a. All right. So what formula, if it's taken to the negative second power, gives us 4/9? If it's taken to the negative first power, gives us 4/3. If it gets to the zero power, is 4. If it's to the first power, it's 12. If it's to the second power, it's 36. Well, if we think about it, a function g to the x would be ab to the x power. The initial value happens when the power is 0. Because what's anything to the 0 power? 1. And 1 times that value is that value. So our initial value, our a, is going to be 4. And if we multiply by 3 every time to go up, our base is going to be 3 to the x power. Okay? 3 to the 4 times 3 to the first is 12. 4 times 3 squared, 4 times 9 is 36. If x is to the negative first power, 3 to the negative first power is the same as 1 over 3. 3 to the negative second power is 1 over 3 squared, which is 1/9. 1/9 times 4 is 4/9. 1/9. 4 times 1/3 is 4/3, and so on. So in the second example, h of x, what's the initial value? 8. And what are we multiplying by each time? 1/4 to the x power. Okay, that's exponential functions. Exponential growth and decay follows this. If b is bigger than 1 and your a is positive, it's an exponential growth function. If a is positive and b is in between 0 and 1, it's an exponential decay function. Okay, that's really, really important. So if something is decaying at 12% per day, we're going to take 100% minus 12% and say that it's 88%. Every day it's 88% of what it was. If it's going down by 12% or 5% or whatever percent it's going down by, you take 100% minus whatever they give you, and that's a percent that we're going to use. Okay. Transforming equations. 2 to the x power. 2 to the 0 power is 2. 2 to the 0 power is 1. This is 1. 2 to the first power is 2. 2 to the second power is 4. So the function looks like this. That's 2 to the x exponential function. Now, I don't know if I can change color. Ooh, I can change color on this. So let's go with blue. So 2 to the x minus 1 power. If it happens up here as a power, it's affecting the x. So the x values are shifted by 1. 1 which way? X minus 1 makes it move 1 to the left or right? To the right by 1. So it's going to look like that. 2 to the negative x. 2 to the negative x is going to affect it. It's going to flip it across the y-axis because the x's are all opposite of what they were before. So you're going to have a dot there, you're going to have a dot there, you're going to have a dot up there. It's going to look like this. That's 2 to the negative x. 3 times 2 to the x. What does 3 do to the function? It affects the x or the y? The y. Everything's 3 times higher than it was with the x. So it's going to cross at 3. And this one is going to be up at 6. So it's going to be like this. Grow dramatically higher, dramatically faster. Okay, everything's 3 times as high. So that was the first one. Shifts everything to the right. The second one flips across the y-axis. And the third one, everything's 3 times higher. All right, the natural base E. E comes from the limit of, as x goes towards infinity, of this function. And you go, well, how does that work? Well, if x is 10, it's 1 plus 1/10 to the 10th power. Somebody on your calculator, take 1.1 raised to the 10th power. 1.1 raised to the 10th power. What do we get?
2.59.
Okay. Let's say x is to the 100. So it's 1 plus 1 over 100 to the 100th power. So this is 1.01 raised to the 100th power. What is that? 2. Is it, are we up to 7 yet? 2.705. Okay. So as x goes towards infinity, this number is going to go towards the number 2.718281828459045 yada 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 yada. Okay? So this is what E is approximately to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 decimals. 2.7182818289045 triangle. Okay? We good with that? All right. So an exponential with a base of E acts like the other exponential functions. And then K is a multiplier. K is the amount of growth that we have. So if K is positive, your exponential function will go up. If K is negative, your exponential function will go down. Exponential growth, exponential decay. That are natural logarithms. So you have your normal E function. E plus 2 would move everything which way? To the left by 2. Negative E to the negative x, you flip it across the axis and you flip it upside down. It's a flip and a flip. So you, from the normal E to the x, Normal e to the x goes like this. So this would go like this, and then you'd flip it over the axis to go like that. E to the x minus 1 takes the e to the x and moves everything down by 1. So there's left 2. This one went left 2. This one goes the opposite, and then it is flipped across the x-axis. And this one goes down by 1. Okay? Transforming graphs. Now, this is something that most of you haven't seen much of. You didn't see it in Algebra 2, I know that. Is a logistic growth function. Okay, logistic growth, there's a limit to how much can grow. In that fish tank, I can't put 1 million fish in that fish tank. Why? Daniel.
Eventually, there would be too many fish, so they'd start spinning out.
And they wouldn't have enough food or enough area to swim or enough oxygen in the water or whatever. There's a limit to exponential growth. You know, you think of exponential growth, it goes like that, but really, in the real world, it goes like that. There's what is called a carrying capacity. There can only be so many humans on Earth. Now, we haven't even come close to reaching that number yet, but in certain ecosystems, you'll see things scale up and then level off. There's only so much grass that can be in your yard, okay? There's only so much soil, so much ground cover, so on, okay? So there's a limiting factor, and C is the limit to the growth. So a logistic growth function is actually more real world than some of the exponential functions that we see. All right. So what are we going to see for problems today? Well, here we go. Pre-calc. Where did we go? Pre-algebra, pre-calc. Boom. Come on. There you are. Okay, we're going to look at functions and determine if they're exponential or not. Is this an exponential function? No, it's a power function because it's a variable to a power, a variable to a number. Number 2, is that an exponential function? Yes, because it's a number to a variable power. A number to a variable power is an exponential function. Is this an exponential function? And I would say no, because it has a variable base. You can't have a variable base and be an exponential function. Okay, is this an exponential function? Number 4. Is this an exponential function? Yep, it sure is. If we put a 0 in, what do we get? If we put a 0 in for x, what do we get? 2. Because 5 to the 0 is 1. 2 times 1 is 2. Okay? 2 is the initial value. When you put a 0 into an exponential function, you should get the initial value. All right. So, let's look at this. What is our exponential function that gives us this? First of all, what is our initial value? What's going to be our initial value here from the chart? 7/6. Exactly. 7/6 is our initial value because that's when x equals 0. How do we get from 7/6 to 7/36? What did we multiply by? 1/6. So it's times 1/6 to the x power. Times 1/6 to the x. Because if you put 1/6 to the negative 1, that's 6. And 6 times 7/6 is 7. Okay, so that's how you build an exponential function. Then you'll have to graph exponential functions. And I apologize right now for Math Excel. Sometimes graphing exponentials on Math Excel are really weird and, well, stupid. But we're going to still, you have to still use their graphing capabilities because you're not going to graph all these out by hand. So 4 to the x power. 4 to the 0 power is what? I'm going to graph this one first. 4 to the 0 power is what? 1. Anything to the 0 power is 1. 4 to the first is 4. So it's going to be a function that looks like this. So then 4 to the x minus 3 does what to that function? Moves it where? To the right by 3. 1, 2, 3 to the right. 1, 2, 3 to the right. It'll go like this. Okay? So it's a shift. 3 units to the right. Okay? All right. 4 to the negative x. So 4 to the x, again, is there and there. It's not very good, but whatever. 4 to the negative x is what? Flipped across which axis? The x-axis or the y-axis? The y-axis. So it's here and it's here. So it'll look like that. Okay. 4 to the x, which one is it? Well, we just graphed it a couple times and it looked like this one. Yeah, you'll have questions on that. 9 to the negative x is the same as 9 to the x, but flipped across the y-axis. So it should look something like this. Whoop, that's 9 to the x. So flip it. So it would be e. And then it's reflected. The graph must be in the shape of b to the x reflected over the y-axis and not shifted at all. So you got to find b. I don't know which one it would be. I think it would be e. Is that what you said? E? Okay. Okay. And then you just keep doing problems like that for a little bit. Now, would this one be exponential growth or exponential decay? Exponential growth or exponential decay? Decay. It's decay because the base is in between 0 and 1. Okay? So since it's a decay, it's going down like this. Okay? So as you're going towards negative infinity, it's going towards infinity. As you're going towards infinity, it goes towards 0 because it's decaying down. Okay? It's decaying down. All right. 3 to the x is less than 8 to the x. When is that true? When is that true? When x is greater than 0 or when x is less than 0? Well, let's just try numbers in here. 3 squared, 8 squared. Is that true or false? That's true. So 2 is bigger than 0, so it must happen when it's bigger than 0. So 1/5. Again, let's try real numbers in here. 1/5 squared is less than 1/2 squared. 1/5 squared is 1/25. Is that less than 1/4? Yep, it is. So this is true when x is greater than 0. Okay. Are they all going to be greater than 0? Nope, not quite. Now to the lovely logistic functions. All right. So 10 is the most that the population can be. That's the limiting factor of the population. So it's going to be a graph that goes up and then levels off, like that one. Okay, it's going to go up and level off. What's our y-intercept? How do we find a y-intercept? Plug 0 in for x. If we plug 0 in for x, we get, sometimes, I tell you what, it has a mind of his own. We plug 0 in for x, we get 10 over 1 plus 4, because 0.8 to the 0 power is 1. 1 times 4 is 4. 4 plus 1 is 5. So 10 over 5 is 2. The y-intercept is 0, 2. Right there is 0, 2. This function has two asymptotes, two horizontal asymptotes. One where it can't go less than 0, and the other one at 10. So the top asymptote is at y equals 10. The bottom asymptote is at y equals 0, because it can't go negative. All right. Here has a limiting factor of 14. 1 plus 6 is 7. So the x-intercept happens at 7, or the y-intercept happens at 7. So 0, 7, 0, 2, because 14 over 2, 14 over 7 is 2. Boy, I can't even talk. 14 over 7 is 2. So that's the y-intercept. Now, what we have to be careful for is, what does this graph look like? Because it has a negative exponent. Okay? Well, let's put in a 1. What's 2 to the negative 4th power? Because this is 2.71818, so it's close to 3. What's 3 to the negative 4th power? It's like 1 over 81. So it's 14 over 1 plus 6 times 1 over 81. So it's 14 divided by 1. This is really close to 14. Okay? Now if we try a number like 10 in here, if we try 10 in for x, that's 3 to the negative 40th power, which is super small. And then 6 times a super small number will be a little bit smaller, and so on. So what's happening to this? As this is getting smaller on the bottom, okay, as this is getting smaller on the bottom, it's 14 over 1 plus 3. I still think it'll probably, if it's C or D, you might have to actually graph this one. I think it's still C. You might have to graph that on your graphing calculator to see. I think it's still C. Bacteria in a petri dish. How many did we start with? 400. How many are present after 4 hours? You just stick a 4 in there and put it into your calculator and solve. Okay? So that's what we're doing today. Exponential functions, getting a start with it. We're going to have logarithms, natural logs this chapter, all that stuff. You've done this in Algebra 2 before. There are just a few new concepts like that logistic function and limiting growth. So there you go. It is out there for you to get started on.